Penicillin was first discovered in 1928 by microbiologist Alexander Fleming. While he was working on bacteria cultures, he noticed that Penicillium notatum had contaminated his cultures. This mold created a clear region in which bacteria colonies were not growing, so he concluded that this substance generated from the mold inhibited bacteria growth. Fleming's original culture plate showed a zone of inhibition around the mold, which proved that this mold secreted a substance which inhibited bacteria growth. In the 1940s, Howard Florey and Ernest Chain successfully managed to isolate penicillin from the mold, something which Alexander Fleming was not able to do being a microbiologist. Following this, large-scale production soon began using fermentation tanks containing corn steep liquor. Penicillin is known to have saved thousands of lives in the later years of war. However, it was not until 1945 that Dorothy Hodgkin determined the exact structure of penicillin G, the major constituent of the mold extract, using X-ray crystallography. Penicillin's structure can closely be compared to a dipeptide formed from two amino acids, cysteine and valine. The molecule contains a 5-membered ring containing sulfur atom known as thiazolidine, a 4-membered ring known as beta-lactam containing a nitrogen and 3 carbon atoms, a carboxylic acid, and an acyl amino acid chain. The beta-lactam ring is the part of the molecule responsible for its antibacterial properties. It has a highly unusual structure, with bond angles reduced to 90 degrees, despite the fact that due to sp2 and sp3 hybridization, the ring seeks to form bond angles of 120 degrees and 105.5 degrees. This puts strains on the bonds, making them weak, which later allows the ring to break easily, which is the key to the activity of this molecule. These beta-lactam rings work by disrupting the formation of cell walls. This is done by inhibiting the action of a bacterial enzyme, transpeptidase. The high reactivity of the amide group in the drug causes the ring to break, binding irreversibly near the active site of the enzyme. This reaction induces the inactive form of the enzyme, preventing polypeptide crosslinks from forming between the mucopeptide chains. These are polymers made of polysaccharide and peptide chains in the cell wall of the bacterium. The diagram on the left shows the active form of the enzyme, which is not inhibited by penicillin. The diagram on the right, however, shows penicillin as the inhibitor, which prevents the reaction from completing and therefore disrupts the formation of cell walls. Without crosslinks being formed, the cell wall can no longer support the bacteria and will eventually burst, as shown below. One problem with penicillin G, the first form of penicillin which was extracted, is that it is broken down by stomach acid. It therefore had to be injected straight into the blood at the time. Since then, however, different forms of penicillin have been developed by modifying the side chain. Some of these altered forms allowed the drug to retain its activity even when ingested directly. Since then, we have been able to synthesize many different forms of penicillin, which all have their own uses. Bacteria resistant to penicillin have become a major problem in medicine. This problem came as early as the 1940s, where resistant bacteria produced enzymes penicillinase or beta-lactamase, which open the beta-lactam ring. Once this ring is broken, the drug loses all of its activity, hence its importance in penicillin's role. As exposure to penicillin increases over time, these resistant bacteria in a population increase due to the non-resistant strains being wiped out. Use of antibiotics in feedstock and patients not complying with prescriptions have added on to this problem, contributing to the development of bacterial resistance. There are several ways in which we can respond to this antibiotic resistance. One of these is the synthesis of different forms of penicillin by modifying the side chain, allowing the drug to withstand penicillinase or beta-lactamase by preventing them from binding. Examples of these include methicillin or oxacillin. Other methods include the control or restriction of the use of antibiotics, making them prescription drugs only. Doctors are often encouraged not to overprescribe antibiotics when other treatments are available. Finally, education of patients is also important to ensure they complete their prescribed treatment with antibiotics. This prevents resistant bacteria prolonging the disease or spreading into the community. To finish, the key ideas of penicillin are: penicillin is an antibiotic produced from fungi or mold. It contains a beta-lactam ring, which is essential to its activity in disrupting cell wall formation. Its unusual structure and bond angles allow it to bond to bacterial enzymes in the cell wall and prevent cross-links from forming. Modifying the side chain of penicillin allows the synthesis of alternate forms with different properties and resistance to penicillinases produced by resistant bacteria. Patient compliance and prescription control are essential to prevent antibacterial resistance from developing further.